Josh will kick us off in a second. Yeah, there we go.
All right, everybody, welcome back to the Summer of Protocols Guest Talk series. This series is part of an 18-week program where a cohort of 34 researchers are exploring the various aspects of protocols. You can find out more at thesummerprotocols.com. Today, we're talking with John Bissell. Our next session is on Tuesday of next week with Alex Komorowski on gardening protocols. The pre-meeting material is linked there in the program calendar at summerprotocols.com. And so with that, I will hand it off to Venkat to introduce John for us today.
All right, I'm going to briefly share my screen to introduce John here. Where are we going here? Okay, so John is the CEO of Origin Materials. This is the website, and I recommend you go look at it. And the reason I'm saying that is the chemical industry is like a little bit more obscure and abstruse, and you actually have to go dig into websites and read some background to even understand what they do and why it matters. And Origin Materials website has like some very interesting details. And this is an interesting follow-on to the last talk from Dara on climate change, because Origin is a materials company that creates carbon materials, plastics, and I'm sure John will talk more about it. But the basic idea is instead of starting with petroleum-based feedstocks, you start with biofeedstocks, and you produce the same materials like PET, but with negative carbon instead of positive carbon. So that's Origin. I've been working with John for, I don't know, 6-7 years now. He calls me out occasionally to their company headquarters in Sacramento for a couple of days to join their retreats and so forth. And the thing I find across all the industries I have consulted in is that the chemical engineering industry is probably the hardest and has the longest learning curve if you're an outsider to it, and it requires the most background and prep to even like be literate enough to hold up your end of like a very shallow conversation. And it's probably the industry where I've done the most background reading just to like even be able to talk to people like John. And I thought I'd recommend a couple of resources in case any of you is interested, because this topic is becoming increasingly important for like climate change and things like that. So 2 email newsletters that I found through John. One is the Polymerist. It's a Substack that covers the basics of the chemical industry. It's written by a PhD in chemistry who kind of like covers the basics in kind of an interesting explanatory way. And another is this newsletter called The Column. Again, a writer I met through John. He's a really young guy who's writing these very useful explainers on how the chemical industry works. And these are the hardest newsletters for me to read. Like I try to keep up and I try to understand what's going on, but man, my mental models are completely inadequate compared to, on a scale of 1 to 10, if my mental models of say the computing or aerospace industries are like 6 or 7 on 10, with chemical engineering, it's like 1 or 2 at best. So these are 2 newsletters I highly recommend if you want to get into this topic. And I also want to recommend this book I've been reading lately, The New Science of Strong Materials, which is somewhere in between chemistry and material science, which today's reading that John recommended kind of gets into a little bit. So yeah, just wanted to point these out. Let me stop sharing here. And yeah, John's been building this company for more than a decade now, because chemical engineering is not like software startups where you can like, I don't know, go from paper napkin to billion-dollar exit in a few years. You actually have to build complex infrastructure, big factories that blow up, and it's complicated. And yeah, I've been following this journey along, and it's been extremely humbling as a consultant to watch this extremely complex project slowly evolve over a decade. And with that, over to you, John. Let's talk about chemistry as a platform and protocols.
All right. So it's sometimes cathartic to hear an industry outsider describe the industry that way, because we feel like it as insiders. We feel like it's hard and it's not straightforward, and there are a lot of twists and turns that aren't obvious. And that is pretty humbling as an insider too. It's just I think in sort of your introductory essay, the unreasonable sufficiency of protocols, you described recycling as one of the more challenging protocols that have to be developed. And that's absolutely true. And yet recycling is probably one of the more straightforward protocols inside the broader chemical industry to develop. So what I'm going to talk about is what we think about all the time, which is I'm going to say protocols, but I think I'm actually kind of making an argument that there is no significant and robust protocol for the chemical industry technology development. There's lots of it once you get into full-scale assets. And I think the chemical industry almost looks sort of uniquely boring once you get to full-scale assets. And by this, I mean big plants, right, that are producing, plastic or solvent or ammonia for fertilizer or something like that. Those sort of start to resemble energy facilities, sort of power plants, where they're traded as basically just cash production machines, almost like annuities. And they get treated and managed a lot that way, which I think is an unfortunate reduction, but that is the way it is. So that's really clear. But in the process of figuring out a new kind of plant to build, which is sort of isomorphic with making a new material or a new process to produce a material, I think, and I was thinking about it quite a bit, I don't think there's any reliable protocol for the development of that. And I'm going to talk about all the different pieces of it that I think I can see and why I think there might be challenges there and why one hasn't developed. I think we need one desperately. The industry is actually, I would argue that the new technology and new materials side of the chemical industry is kind of dying. And this is actually somewhat broadly known inside the industry. And yet right now we need new materials that work better more than we ever have, probably. We're finding out, you hear about PFAS or perfluoroalkyl substances, which are the forever chemicals that we now find everywhere. They're in everybody. And they do seem to have meaningful effects on our metabolism and our human development. That's at its most fundamental level. That is not a regulatory problem. That's a materials development problem. We made the wrong material, and we've been making it for a long time. We being as a species, and we need to find better replacements, but sort of nobody wants to do it, or nobody knows how to do it. Same thing for phthalates that everybody's heard about, or BPA. Those are both human health issues as well. And then climate change. A huge proportion of the emissions associated with humankind are based on either the production of materials or the performance of materials in applications like energy. And I'll talk a little bit about that too. So I think what I'm going to go through is, I wish I could say that it's a really clear description of the protocol for developing technology in the chemical industry. But I think it's actually more of an argument that we don't really have one, and boy, do we notice it. So I described this talk as sort of matter manipulation or disassembly, reassembly, which is really how we think about the world in lay terms. And I thought it was sort of useful even for me. This is a little bit trite, but it was useful for me even to just understand what's the definition of chemistry, because I sort of live it and breathe it all the time, that it's not something I think about. And so it's kind of a nice description to say it's the identification of substances of which matter is composed. This is the Google definition. The ways they interact, combine, and change, and processes to form new substances. And if you think about that, I mean, that's a pretty important class of human activities. It's, basically, we describe the chemical industry as the production of all physical goods, right? You could think of even like a pen is the company that makes the pen and designs the pen and sells the pen is actually kind of just a channel to market for the chemical industry. And it's useful, I think, again, to think about the impact of the chemical industry and why it's the motivation for being able to develop new technology and materials here as important is because of that. Everything you deal with, the chair, the apparel that you're wearing, the face moisturizer that you put on, the shampoo you use, the food you eat, all of that stuff is the result of the chemical industry and basically what I'm going to talk about in a few minutes. The other thing that I think is really useful, and I'm gonna try to build a little bit of intuition for you guys, even though I realize that you're non-technical or from my definition of technical, most people are non-technical, and so I'm going to try to do that from the bottom up a bit. And I thought this is a Feynman quote, and some of you guys may recognize it, but it's the bottom is. But this is how he responded to a thought experiment, which is basically if there were some sort of apocalypse and you could only leave one piece of knowledge or instruction behind for the humans that survive, what would be the most useful thing to tell them? And this was his quote on that, which is that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. And essentially from that, you can sort of understand or ask really interesting questions that would help you understand effectively everything that we've learned, in the last 150 years about physics and chemistry. So I'm going to start there. We call this, by the way, this is the foundation of the way that most chemists, well, I'll say most good chemists think about the world, which is we think about things at the molecular level. So we think about little balls moving around doing stuff, and we attribute behaviors and personalities effectively to those little balls. Okay, why might it matter to have a really effective chemical protocol or chemical technology development protocol? I think the sort of fantastic picture of this is a little bit like replicators from Star Trek, or I now forget the exact term that he used, the sort of matter pipelines from Diamond Age, where you can create whatever you wanted, and sort of like a data pipeline into your house, you have a matter pipeline. And then I think maybe a little bit more germane to today is, infinitely recyclable, renewable, non-toxic, general purpose materials. I think we all sort of want that. I think society keeps asking for something like that, and we don't have it. And I think if we're going to be successful in these kinds of endeavors, we need to do better than we have historically in chemical technology development. Because right now, every single time new technology is developed in the chemical industry, or let's say by our species in the chemical industry, it's its own unique journey to maturity, and it has many near fatal experiences and barely makes it out. And I could tell you the individual unique story of almost every single major chemical building block that's made now by human beings. And I think that means that there aren't enough of them, and it's too idiosyncratic how they end up getting to scale. Okay, so I'm gonna embark upon a quick journey through how chemists think about molecules and atoms. And the reason for that is I think it's important to understand why I think we don't have a good, reliable protocol. And I think the purpose of a protocol at least the way I think about it, is for our industry would be to enable predictable behavior upon which more complicated systems can be built, right? This is the generative qualifier. But I think this is one of the key parts that the chemical technology development world is failing at. Okay, so don't worry too much about some of the numbers. They're intended to be sort of gestalt or directional numbers. And I've made a ton of simplifications that are sort of ridiculous in this model, but I'm trying to really focus you guys in on getting one particular frame of mind. So, the thing to understand about the chemical industry is that, or chemistry in general, is that it's actually founded on one of the best and most predictive systems of physics or mathematics that the human species has, which is quantum mechanics, or you could call it quantum field theory or quantum electrodynamics. These are all just different sort of shades of it, but I'll be simple and call it quantum mechanics. It works really, really well. It works so well that for about 100 years, it's been hard to find places where it didn't work, which has actually led to some probably pathological behavior in the world of physics, because people can't find something that's not working, so they're sort of making stuff up. So it works unbelievably well. And so the natural question is, well, why doesn't that translate up to the macro layer? Well, I talked about chemistry at human scale, and that's a really important qualifier, because chemistry at the atomic scale is actually really quite straightforward these days. We sort of understand how a lot of that works at a single atom scale, but it gets complicated really fast. And that's what I want to give you guys a little bit of an intuition around. And so by the time you get to anything remotely approaching the human scale, it's almost completely unpredictable using our really rigorous quantum mechanical understanding and computations. And I'm just going to give you a really short version of that. So, if you have a hydrogen atom, you basically have this is sort of my boundary condition for the abstraction of the hydrogen atom. You have two particles. As you're going through and solving quantitatively what this thing can do, right? Basically how it's going to behave in any given situation. You basically have 6 variables in your partial differential equation, and you're sort of my baseline proportionality there for a hydrogen atom means you've got about 36 sort of minimum computational steps. That's pretty easy. We can do that all the time. We've been able to use that for a long time. Okay, well, if you have 2 hydrogen atoms, you went from 36 to about 600. And that already got really quite complicated. Now, it turns out that there are some assumptions you can make, and now we have pretty good computational capability. And so you can identify that they're going to form a bond. And this hydrogen molecule actually ends up being the simplest molecule, generally speaking. So the hydrogen atom is the simplest atom in the universe that we know of, and the hydrogen molecule, a diatomic hydrogen molecule, is the simplest atom in the universe, or molecule in the universe, as far as we know. Now, what's really interesting is when you start to get to what we would still consider a relatively small scale phenomena. So let's look at like a battery cross section. So with batteries are a sheet that's been rolled up. So what you typically see with a battery is the coil, the rolled up coil. But if you can imagine unrolling that onto a sheet, and that's a very thin sheet. So a battery sheet's usually, maybe it's a couple of millimeters thick. And then, imagine that you're just looking at a column. And in this case, I'm talking about, a couple angstrom column. It's just this many atoms across. And let's imagine that we want to predict, well, what happens when I intercalate lithium atoms in between a bunch of the carbon atoms, right? Which is what's basically happening reversibly with batteries in order to store and then generate energy, right? So this is in the world of chemicals, this is a remarkably simple model for what's going on. Now, I could put a bunch of complications on it, and we could throw together sort of what's the structure and how many interstitial dislocations are there, and there's all sorts of stuff that's weird about it that isn't this. But generally speaking, let's just call it this. And maybe what we want to know is, how much energy am I going to generate when my lithium, or am I going to store or generate when my lithium intercalates with the carbon or leaves? I might want to know how frequently does my lithium not intercalate well and instead reacts in some fashion with something else that's in the carbon? Because at that point, my battery is going to start to decline in performance, right? It's not going to work anymore. And those are all really useful things to understand, because if I don't know those things, then I have to go build stuff to find out. So if I can figure it out on paper, that's useful. And what I'll talk about in a little while is, it turns out that generally speaking, the space of not knowing, the uncertainty around a bunch of those things is large enough that it can individually cause these systems to succeed or fail. So, for example, if I want to switch out sodium for lithium, right? Sodium batteries are a big thing. What I want to know is, how's it going to perform in this system generally? And I'd like to be able to do a bunch of that work on paper and computationally, instead of having to go build, the perhaps tens or hundreds of millions of dollars worth of systems to actually go figure this out. experimentally. And the problem is, if I take this simple system and I punch it through and look at a millimeter thick, or maybe even less than that thick, cross-section of this little itty bitty system. So we're talking about 1/1,000,000th or 1/1,000,000,000th of the total volume of a single battery sheet. What I find is that my proportional computational steps exploded extraordinarily rapidly. And so almost immediately, it becomes infeasible to use quantum mechanics, which is our really nice rigorous understanding of the way that the physical world works, at any level that we would consider practical. And that's true for what we call the application, which is something like this, where you're trying to say, like, I want my battery to work better. And it's true also for the synthetic side. So when we want to make something new, so for example, let's say I want to make the graphite that the lithium is going to intercalate into, that has sort of a characteristic scale to it as well. And in both cases, it's almost completely infeasible, except in very, very special cases, that you can use our rigorous understanding of the physical world. And so instead, what we end up doing is building a completely different set of rules, essentially, for how systems operate at different scales. And as those scales get bigger, they tend to get more and more divorced from our sort of foundational underlying understanding of the world, which is quantum mechanics or quantum field theory. So sometimes I call, at origin, we call that physical chemistry. That's not strictly true. There's definitions of what physical chemistry is and all the rest of it, but I'm not going to go through the entire taxonomy of chemistry with you guys. But so let's call it sort of physical chemistry and beyond, everything up. It's generally wrong, right? It's wrong in sometimes important ways and sometimes not very important ways. You hope that they're not very important. They're both calculable at the atomic scale, but of course the key is that we can actually do calculations at the human scale with these kinds of systems. And this physical chemistry and everything that happens above it is really that is what people are trying to solve in order to build a robust protocol for how you can actually assess, develop, apply new chemical technologies. And I would make the argument, I think, that it is the inconsistent predictive capability of this system that causes so much trouble in that area. Okay, so let me see here. I want to make sure I hit all my points on this. Yeah. Oh, there's sort of a fun story that I enjoyed around some of this stuff too. Actually, I guess it's on this that is worth going and reading more about if you're interested in this sort of thing. But in the development of our modern understanding of quantum field theory, particularly with quantum electrodynamics, there was a really interesting example of how unbelievably incalculable a lot of these systems are, or even at the atomic scale, sometimes these systems are. Which is Feynman obviously got the Nobel Prize for development of quantum electrodynamics, and then so did two other people. One of them is Julian Schwinger, and they had two completely different approaches. This is a really interesting case of convergent development of a particular scientific breakthrough. So Feynman developed a predictive system that was completely divorced from mathematics for predicting behavior in quantum electrodynamics, and these are called Feynman diagrams. And there's a whole system of arcane rules, but that is actually usable to predict what's going to happen in quantum electrodynamics with a given set of particles. You can sort of draw these bizarre diagrams that have very specific rules to them, and it will compute for you and tell you what the outcome is on the other side of this sort of this matter transaction. The problem was nobody could understand, they couldn't verify if this was something that made sense with respect to the rest of the more mathematically oriented quantum mechanical principles. And there was this other guy, Julian Schwinger, who built up an incredibly rigorous mathematical analytical framework for what the right answers should be in quantum electrodynamics, but they were completely incomputable, even for small systems. And the two of them were fighting for almost a decade, I think, quite viciously about who was right. It was a big schism in physics. It turned out that they were identical. So it took a guy, Freeman Dyson, whom some of you guys have probably heard about because of his son's writing, George Dyson, who wrote Turing's Cathedral, for example. But so Freeman Dyson demonstrated that the Feynman diagrams are actually mathematically equivalent to Schwinger's work, which meant that they were both right, but approaching it from a completely different direction. One usable, the other one provable or legible, let's say, which I think is sort of interesting also for some of the large language models that are going on right now, which of course are illegible, but workable. Okay. So that all said, that's why we don't just have, even though we've got great physics around this, we don't just have the right answer that just works. We have to build an entirely new system that is often physically, or I should say mathematically consistent with quantum mechanical systems in idealized regimes, but we never work as people who actually make stuff. We never work in idealized regimes, and so the accuracy. And so the second thing is the accuracy of sort of the predictions of physical and synthetic chemistry. Those are rarely within the economic tolerances of product. So, the uncertainty ranges from unbelievably profitable to dead on arrival, right? For product economics. And as a consequence, most product and process development in our world is very empirical. Of course, it's guided by physical chemical principles. We think about all this stuff. Obviously, I'm a practitioner in the field, and yet I start most of my thinking with sort of pretty rigorous quantum mechanical understanding of the world. But the reality is that we do hundreds of thousands of hours and more practically millions of hours of work trying to understand and to explore the systems that we're developing empirically, right? Experimentally, because there's no other option. Even when you're being really, really efficient about the way that you're designing your experiments and measuring your way through the system and trying to develop new aspects to the system, it still is extremely empirical. And that, as I said, makes it really, really expensive. You can imagine what millions of hours of extremely capable, highly trained people's time costs, and that's not even accounting for the capital side. Okay, so if none of this works, we obviously, we all live in the modern world where there's a bunch of physical goods that are very interesting that we deal with all the time. So we haven't just given up. There must be something that happens. And so I want to walk you guys through a specific example of sort of what the technology development and industrialization of that technology has looked at in a particular case. So this is a case that is we would look back now and say is remarkably tractable. It's actually from circa World War I. It's the Haber-Bosch synthesis of ammonia. So the Haber-Bosch synthesis of ammonia is probably the most important chemical process that was ever developed by humankind. Generally speaking, if we hadn't developed this, there are probably about 3.5 billion humans that wouldn't be feedable off of our existing arable land. So we either would have had to have clear cut a lot more land than we already have, or a lot of people would have died of starvation over the course of the last 100 years. So something like, whatever, a third of the human population is sustained by the fact that we developed this process. And as a consequence, about 80% of the nitrogen atoms in your body actually came from a Haber-Bosch process. So it's an incredibly important sort of underpinning of modern human civilization. And it turns out that the way you make that is with really simple molecules, nitrogen and hydrogen. We know how to make those. Nitrogen is most of the air, and hydrogen you can make by a variety of means. The one that you do usually in elementary school is electrolysis of water into hydrogen and oxygen. But we typically make it actually from natural gas now. We steam methane to reform it, make it. And that's how it's made usually for the Haber-Bosch process. And what's interesting about this is when they developed this, it was done almost entirely empirically. It was actually, quantum mechanics was in development and meaningfully so around the same time that this process was being developed. But while Haber and Bosch, who were a chemist and an engineer, were remarkably bright, I have never read that they actually kept abreast of the modern at that time sort of modern physical developments that were going on in Copenhagen, for example. And so I suspect that they were not thinking at all about this as a quantum mechanical process. My guess is that this was almost purely empirical. So they had probably a good understanding of what sort of the atomic theory was, but that might have been it, aside from the empirical relations between everything. And yet they developed a process that was, is not, we don't run it that much differently now than they developed it 100 years ago. And it's run at massive scale. So it's one of the things that we should have done better if one could do better. But we don't. So I think that, I guess I use that as an interesting example to say, really, we may not have advanced very far beyond the sort of pre-modern physics era of chemical technology development, even though all of the chemists and engineers walking around have a pretty good understanding of that sort of modern physics these days, which I think is kind of interesting and maybe a little scary. But so what's interesting here is you might want to be able to predict, for example, what catalyst would be the right catalyst to use here, right? So this is what's happening here is you have nitrogen and hydrogen absorbs on, well, technically adsorbs, but that's not usually a term people are used to, but it sort of attaches itself to the surface of what's basically a metal powder. And then it reacts on the surface of the powder, and then it wanders off as ammonia, which is the species that we care about. And, one of the critical questions is, well, what is my catalyst? There are lots of different elements in the periodic table. It turns out that a lot of those elements will act differently if mixed with 2 or 3 other elements. And so you have an enormous number of different combinations of extremely rare elements. And then, of course, you have lots of different temperatures and pressures and other things that you can do to play around with this reaction to make it go. And generally speaking, there are lots of reactions that won't go at one temperature and will go at another one, and that won't go at all on one catalyst and will go on a different catalyst. And so there are lots of sort of magic catalysts. It never works until you find the one single right catalyst on the entire periodic table, and then boom, suddenly it's good enough that it's an industrial process. So you would like to be able to predict these sorts of things, but I'll tell you, in this case, they ended up using osmium as their catalyst, which the story goes that they had accidentally left a piece of osmium in the research reactor that they were developing this process from. And that one batch worked, and every other batch was completely infeasible. And they eventually went back and picked out that there was like an osmium screw. Why they would have an osmium screw wandering around there, I don't know, but this is the way the story goes. That there was an osmium screw loose in the reactor that they had that caused the successful experimental catalysis. But so you can see this is a very sort of random walk and seize opportunities as you run into them kind of process, which makes it very difficult to make reliable and predictable and something that's interchangeable. It's extremely idiosyncratic. Let me see here. Okay, so I think I've got another one. Yeah, so there are a bunch of different critical parameters that you might be interested in. I'm not going to go through all of these. They're sort of an exercise left for the listener in case you guys feel like Googling some of these things or have an understanding of them. But the point is that any one of these could be perhaps 5 or 10% different, and if it is, the whole system falls apart. Whatever you build, that as you drive, some of you guys have, I'm sure, driven through Sacramento, going up to Tahoe. I don't know where everybody is. There are oil refineries all over the world, but that's a particularly notable one. as you drive down the freeway and you see a gigantic oil refinery, what's going on is this kind of process somewhere in some form, not necessarily ammonia, but other things. And the design of that gigantic, sometimes a refinery might be $5 or $10 billion in capex. That gigantic facility is dependent upon highly precise understanding and measurement and predictive capability of these individual little things, these different parameters over here. If anybody's wondering why it switched from iron oxide to osmium between these two, it's because I couldn't remember what the catalyst was when I was putting these slides together. And I only looked later and forgot to change this slide. So nothing intended with the difference. Okay, so what is the way that we do in the industry bulk matter synthesis then, or bulk chemical synthesis? Well, the way that, as a consequence of all the things that I've just described, the way that it has ended up is this. Now, you don't need to be able to see all the little individual details here. This is sort of a take the gestalt impression, but basically what happens is we've built this industry that is based on building blocks. Almost every building block that the industry makes is here. The exceptions would be the inorganic ones like iron, or which is quite large scale, or silica, aluminum, a couple others, not many. And here, what's happening is, this is basically running left to right. We start with raw materials, crude oil and natural gas. Those get broken down in a refinery here into different kinds of naphtha, liquefied propane gas, methane, ethane, etc. Natural gas similarly gets fractionated down, and then you make a couple core building blocks: xylene, toluene, benzene, propylene, and ethylene are sort of the core. And then you make maybe 36 additional building blocks downstream, and that is, it is not too much of an exaggeration to say almost every single thing that you use and touch is produced from, and each of these is a molecule type. Every single thing that you use and touch is built from these 36 molecules, give or take. The exceptions, of course, as I said, are metals, of which there are not very many that are isolated. Usually that's aluminum, iron, nickel. That's about it. And silica, and then there's one other really unusual chain, which is the silicone chain is a really interesting chain. But otherwise, it's all on this chart. And what's happened is, in each of these areas, there's actually an incredibly robust protocol for development on that particular building block. And it's because the specification for that individual intermediate, and this is what I'm saying is more true as you go right than it is as you go left. The specification for each of those intermediates, those building blocks, is more fixed, and that makes it more predictable. And so you see lots of development that happens in the chemical industry down here on the right side, because these are very predictive species, right? So if I want to make different kinds of polyurethane, I can basically treat it almost like cooking. I sort of know the general parameters that this thing is going to operate in, and I've got 25 different versions of my ingredients that I can sort of play around with, and it's all going to kind of turn out the way that I want. And then on the left side, it becomes really rigid. So, each of these species are essentially products by processes. You have to make it one particular way in order to make one particular product with its own special contingent of minor impurities, things that are 1 part per million or 1 part per billion in some cases. But everybody knows that those are predictable and operate the same way. And so Venkat was talking about what we're doing at Origin. What we're doing is we're trying to stand up not just a new one of these down here, we're trying to stand up an entirely new chain here. So you don't have to make things only from crude oil and natural gas, which, by the way, there is literally no other way to make almost all of the organic materials that we use as a species right now. It doesn't exist. And so people talk about decarbonization of these, but it's until you develop fundamentally new technologies to build new stacks, right? Matter stacks, basically. You cannot do it. You will still use crude oil and natural gas. There is no choice. And yet, in order to develop that entirely new stack, you have to be able to compete economically and on performance and predictably with all of the things that have been developed here on this other system. And that is very difficult and very expensive. And it's the reason why it is so difficult to decarbonize a lot of these systems. Energy, interestingly, is easier for a whole lot of reasons. But the most important one is that, generally speaking, an electron's an electron. In this world, ethylene is the exchanged species. That's the thing you're making that you're passing to somebody else that has value. It's sort of the equivalent of an electron in the energy world. Ethylene is not. One ethylene is not necessarily equivalent to another tank of ethylene if you don't make them the same way. You have to be very careful about that. And that is built into the way that the risk is managed through the whole chain. It's very interesting. So consequently, there is no sort of protocol for until you get probably, I'd say, somewhere around here. This cut point is where you start to see what we would think of usually as protocols where you can actually, it starts to satisfy all of those criteria. Okay, so that's what we've got. We've talked about why it matters. We've talked about why it tends to be this way, why it's so complicated, why it tends to be expensive to do this. I'm going to go through a couple attempts in the industry to build more predictable technology development systems. I'm going to go through them somewhat quickly, although they're really interesting to go look into. One that is probably the most explicit, or the most explicit attempt to do this, is called click chemistry. It was developed by a guy named Barry Sharpless, who's legendary in the chemical industry. And it was essentially a specification of all of the things, the characteristics of a reaction and a process. So a reaction is the chemistry, and a process is what you're doing to run that chemistry. I should have said this in the beginning. You can think of a lot of the macro chemistry stuff as like cooking. So if you want to build, replace, molecule with starch, right? If you're, or flour, if you're making a roux or something like that, and replace process with cooking instructions, maybe something like that, reactants or ingredients. And that analogy actually holds for a surprisingly deep level of detail. So he specified a whole bunch of characteristics of your reactions and your processes that are associated with them. And if you do all of those things, if you can find things that do all of that, then you have a spectacularly predictable protocol. It works great. You can basically mix and match, and you know exactly how it's going to work. And people did some really interesting stuff on it. The challenge is when you apply all of these filtering characteristics, at least so far, and this is kind of a hot area of research in chemicals, is to go look for reactions and processes that fit these characteristics. If you can use only reactions that conform to this set of criteria, it works great. It is you can stand things up quickly and cleanly, and they work the way you want. It's a wonderful system. The problem is there aren't very many reactions that actually conform to that, and there are so few that I would say there hasn't been any meaningful economic activity, to my knowledge, outside of pharmaceuticals that's resulted from this attempt to develop a protocol, a synthetic protocol, which is unfortunate because pharmaceutical synthesis is not a hard problem. We can spend almost arbitrary amounts of money on pharmaceutical synthesis because the product is so valuable. So I think, but I have hope that maybe this will be interesting someday. It just might take a little while. So another interesting area where people have tried to develop a more predictive system upon which you can sort of reliably do more complicated things is electrochemistry. So electrochemistry is actually a really old technology. It was one of the first chemical synthesis technologies. And it basically uses electrons as a reagent. What's interesting about this is it's much more selective than the way we do chemistry otherwise, which is basically sort of, like cooking, mixing things together. The challenge is that it's not quite it doesn't simplify it quite as much as we want, although it's much more, it is still much simpler. There are still a lot of unpredictable elements that you have to do just purely empirically. But part of that is because electricity still isn't quite cheap enough. So I think I personally am quite bullish on electrochemistry as a platform for sort of generalized matter synthesis over the next, say, 50 to 100 years, because I think electricity really will get that cheap. So I think this could be sort of a major trend in the way that materials are made, and this would be huge. This linked with renewables. A lot of people are betting on the idea that this is the answer. The one that I think is probably maybe most interesting is biology. So biology is essentially a custom matter or bespoke matter synthesis protocol. So in this particular case, the stipulations are that the reaction has to proceed in water. It has to, the system must be dilute. You can only use polyamides or nylon. All proteins are nylons, by the way, in case anybody wants a weird fact to talk about at a cocktail party. Your nylon is made out of the exact same chemical bond structure as all proteins and enzymes. Enzymes are proteins. And so you have to only use polyamides or as your catalyst structures. And then, of course, you're using your nucleosides, right? DNA and RNA as your programming interface. It works spectacularly well. Obviously, it built itself. The problem is, and the reason why it hasn't sort of taken off for matter manufacturing is that it turns out that water and dilute are really constraining requirements. So as a consequence, it's circa 10 to 1,000 times more efficient to run a synthetic sort of synthesis system outside of water and concentrated than it is to run it in water and dilute. And so that's why you haven't seen synthetic biology take over the world yet. Maybe it will, but there are some thermodynamic limitations that seem to be pretty challenging to overcome. But I think there's a lot to be learned here. Another approach that I'm something of a proponent of is sort of, I call it, or actually, I think Venkat actually named it the eigenmaterials approach. But it's the idea here is you actually try to migrate all of the variability in materials out of the actual chemical layer. So you're no longer trying to change your materials to get different properties. You're using the mechanical layer. So how you structure those materials in order to get differentiated performance. And this is actually working pretty well. It's early days, but some of the things that you'll see that are sort of indications of this or ripple effects from this are the argument for monomaterials in recycling. So anytime you see people talk about needing monomaterials, or that's really an outflow of this sort of eigenmaterials argument. And the boat that I showed here is called the Plastiki. It was built by a guy, David de Rothschild, who is an adventurer, but he took entirely recycled PVC or PET, bottles, and built this pontoon boat and then sailed it across the Pacific. And the idea here was to demonstrate that all of the things that you'd usually make out of metal or nylon cord or carbon fiber or whatever else, you actually can make it out of PET and it will perform well if you do the mechanical structuring correctly. And I think it certainly made an impact on me when he did this. A lot of people who are very knowledgeable about materials look at this and say, you couldn't do that. It's a little bit like saying, go build the SR-71 Blackbird out of recycled PET bottles. The intuition of most people that are aerospace designers would be to say that's not possible. Now this is less extreme than that, but I think it's a really interesting avenue. And the idea is to engineer the material, the small set of materials that we're going to use, since you no longer have to rely on the materials to get differentiated properties. Your small set of materials that you're going to use, you can invest enormous amounts in making sure that those are synthesized in the way you want. They're decarbonized, they're low toxicity, all those kinds of things. So this is in some ways, actually, this is almost an abandonment of the idea that you can develop a robust new chemical technology protocol. It's saying, stop worrying about that and do it all in the mechanical layer. So I as part of this, and this will be my last comment before I open it up for questions. As part of writing this talk, I listened to Sarah Perry's talk. I would have liked to listen to Dara's also, but I didn't. He gave his talk after I'd finished writing this one. But she mentioned processes as alibi, protocols as alibi. And there is one of those in the chemical industry, and it's the sort of conventional stage gate development process. Many chemicals folks would argue that there's absolutely a protocol for new technology development in the chemical industry. It is the stage gate process, development process. And it has successfully produced, to my knowledge, no meaningful technologies that have made it to scale since it was instituted about 50 years ago. And so I think that, and yet people will tell you that this is the gold standard for how to do new technology development in the chemical industry. And so in some ways, that's sort of my proof positive that I think we do not have a really robust, maybe I might even constrain it to new platform technology development process or protocol in the industry. So with that, I'll open up for questions.
Amazing. Thank you so much, John. Very in-depth discussion around the materials creation. So yeah, we'll open up for questions. If anyone has some questions for John, feel free to throw your hand up in the chat.
And also, I'll say, I know I tend to talk at a somewhat technical level. Don't feel like you have to operate at that level. I just can't help it sometimes. So you can ask about stuff that's even related to the chemical industry if you want.
Cool. Dorian, you have a question?
Let's see if I get that unmute in the first try. I always go for the lower hand. So what does the mechanical layer look like in detail? Like if you want to make a boat, like what does that
mean?
What does that mean? Yeah.
So the example that I use for this most often is a corrugated cardboard. So
okay.
If you have a sheet of paper, it's flimsy, right?
Yeah.
But if you corrugate it,
mm-hmm.
and then you lay some constraining paper layers on top, you get something that's actually quite stiff.
Right.
So that would be a migration of the material property development into the mechanical layer, right? The way you organize your material is driving the properties of it rather than the material itself. Because I could also just give you an aluminum sheet and it'll give you the stiffness that you're looking for out of the corrugation of the paper. Okay. Another example of this would be have you ever seen the winding walls? It's another corrugation example, but winding walls, right? That's a you could go get bigger rocks that are to comprise that and then only have to do one layer of stones and be straight, or you can do two stones, or you can have it wind and then it self-reinforces and you can use a thinner layer of smaller stones in order to build the.
Right. So like, I guess there's a lot of stuff in 3D printing and like stuff like sphere packing and all that kind of good math stuff too in there.
Absolutely. And there's actually, so there are some interesting material properties that are unexploited in a lot of this. So PET is what your water bottle is made out of. It's a really interesting material. So for example, if you try to, so PET has an interesting property where if you stretch it, it gets stronger. And it does that in a very specific way. And that's actually what enables you to blow a bottle. So if you were trying to blow a bottle out of PET and it didn't have this property, it would just pop. Because as it thins in a particular spot, it gets weaker and that part stretches more and it thins faster. So that's, an infinite thinning as a whole, right? And so that's a positive reinforcement or positive feedback loop that causes holes. PET has this what's called strain crystallization behavior, where as it thins to a certain point, it gets much stronger. And so that provides the negative feedback loop that you need to actually get a homogeneous length of material or thickness of the material all the way around the bottle. So there's properties like that too. It's not always just the orientation of it, but the way that you process that material can also change its properties pretty significantly. And a lot of those are underexploited.
So you're kind of looking, and to what extent is there a taxonomy of this or some kind of computable structure that you can be like, okay, well, we just
yeah,
what these kind of results, like, is that what you're?
And that's much more doable. So a lot of times we already know a lot of the core behaviors, and once you get into that materials layer, it becomes like or the manipulation materials, it becomes much more computable using things like computational fluid dynamics or CFD software is pretty robust. All those sorts of things. It becomes more straightforward.
Venkat, you have a question?
Yeah. So John, normally in these talks, I try to hold my questions to the end to give our researchers a chance to ask questions first. But in this case, it took me so long in talking with you to even learn to ask any meaningful questions that I figured I'd throw in a couple of comments early. So two remarks you made to me very early on when we started working together have stuck in my head as good mental models. One is you said Origin was trying to almost be the AWS for chemistry, and it was mind blowing for me to even think of chemistry as a platform technology. And you guys were using the terms platform molecules and platform chemicals, and I was I can't connect the dots between the idea of a platform and a particular molecule. And I think the other interesting revealing fact or idea you guys were using were in a high school chemistry level, which people like me are familiar with, all chemicals are kind of like the soup of things that you write equations about. But you guys think in almost economics terms of benzene is the currency of petrochemistry, and you guys are trying to make furans, which are 5 carbon rings, as the kind of new token. So I'm trying to connect the dots to cryptocurrencies here. But yeah, you kind of almost think of economic token chemicals that organize the chemical economy. So these are some useful mental models I had. But the one question I'll throw in there is, how has the AWS for chemistry idea fared in the 10 years you've kind of been thinking about that?
Yeah, so it's really interesting. I actually had I was going to try to build that up in this talk too, but I started running out of time. I thought I was going to saturate my my available time. So it's actually going. I'd say we haven't been investing in it as much as we wanted to. But I'd say we're getting indicators that it's more doable than I would have expected. And then the foundation for that, and the reason actually why I gave the pre-reading that I did, well, one of the reasons, George Whiteside's the guy who wrote that paper that I gave the pre-reading, is probably sort of the most legendary living non-pharmaceutical chemist. So he's the patriarch effectively of academic chemistry these days. And I think that the foundation of that AWS for chemicals system is analytical capability. So the analytical sciences are going to be the foundation of that. And I think, so the question that we often were asking ourselves is, why hasn't that already happened if that's the case? And it turns out the answer is that the analytical capability of existing chemical companies is absolutely horrendous. If they aren't operating their analysis on their own specific platform, it's almost totally non-generalizable, which blew our mind. So we're actually pretty bullish on it, but limited resources. We haven't quite gotten there yet.
Awesome. Do you have time for one more question, John?
Yeah, I can run over by about little while if people have.
Cool. Rafa?
So I'm kind of curious about your so you talked about the incomputable nature of kind of quantum mechanics. I'm kind of thinking about some of the last solution that you presented on using mechanical solutions with more generalized materials. And based on your knowledge, is that a computable problem as well, or is that also an incomputable problem? I don't even know if the question makes sense, but I'm trying to tie those two concepts together.
Yeah, no, it does make sense. So I'd say understanding what properties materials might have that we could use is probably not very computable. And that's challenging. But the benefit is we've been using a lot of these materials for a long time, 100 years, right? And so there actually is a pretty good understanding of how most of these materials behave because they're out there. There's 200 million tons of polyethylene that gets used in the world in an uncountable number of applications. And so there's a lot of either data or knowledge about how this stuff works. And the question I think that's interesting about that is how do you take all of that and stop trying to make new materials and instead apply that for how to manipulate the materials using those properties that we've observed? And that is a much more manageable kind of computable project.
And just a quick follow-up to that. When you're talking about mechanical solutions too, does that include, for example, like nanomaterial mechanics? So like when you're taking the same material, but you're doing layers or like corrugated.
Yes.
Okay, cool.
Yes, exactly. And that's really interesting because when you start to change the surface area to volume ratios, I mean, you guys have probably all heard of, well, maybe not. I don't know, the power square law or square cube law, which is, so square cube law is the power or the force or inertia of a given item increases with or decreases with the cube of the radius, whereas the surface area increases with the, did I get that right? Square. But the square of the radius. And so as a consequence, when you go really small, your surface area gets gigantic relative to your power generation capability, and vice versa when you go up. And so you get some, for particles and molecules and materials, you get some really different behaviors when you're changing that over several orders of magnitude.
Yeah, and that brings us back to that's incomputable right now. So that's uncomputable right now.
Right. It can be very difficult to understand what that.
Yeah, because I remember when I was doing research in college, like the only way to test the nanomaterial was like you could theorize like some of it, but you would have to synthesize it to test it. Like there was no way to do the matrix multiplications, like to actually check what the behavior was. Yeah,
exactly. That's the problem writ large for the whole industry. In fact, so I'll give you a concrete example for our plant. We have a plant that we just built. It's a $150 million plant that we just built up in Canada. And I just got back from there last night. We're commissioning it and starting it up this month. That plant is the first time that we will be able to make quantities of samples that certain applications can even test. So, you give them in the application side, when people are actually using this stuff to do things, often if you give them a gram or a kilogram, they just can't do anything with it. You have to send them a rail car, 100 tons of material before they can evaluate whether that material is interesting. And so you can imagine to be able to even run the first fail-fast experiment, you need $150 million and 10 years worth of development, right? Not 10 man years, probably about 500 man years of development. That's kind of insane, right? And it gets at why some of these problems are so intractable when the industry is not working the way you want it to.
Awesome. Anybody else have any last minute questions that we would like to ask John?
All right. Thanks, guys.
Awesome. Thank you again so much, John. This has been super interesting and informative, and we will see you all next Tuesday at 11 a.m. Eastern Standard Time for a talk with Alex Komorowski. Bye-bye.